All right. A very good evening to all of you people. Welcome to this GMAT Quant webinar here on the YouTube channel for GMAT Club. Uh, as you know, this webinar is on the concept of remainders related to the number system. At the outset, I'd like to tell all of you that I'm really excited to be on this webinar. It's been almost a month and a half since I did my last webinar on quant, and I'm really excited to take up this webinar. This is also one of my personal favorites as a topic. I really enjoy solving the questions on remainders. So that's another reason why I'm equally excited to be on this webinar. And I hope all of you are as excited as I am to be on this webinar. And in this webinar, I'll be covering some fundamental concepts which are required to, which you need to know to be able to solve remainder questions. I have about 10 to 12 really good questions on remainders. And as we solve these questions, you'll get an insight into how you need to tweak your approach based on the question, and you'll get to learn some really interesting and useful strategies that can help you ace the questions on remainders on the GMAT. Having talked about GMAT, the questions on remainders on the GMAT can be diverse in nature, in terms of difficulty level, in terms of how the question is modeled, and also in terms of what is tested. So it can be quite diverse, and therefore you need to have these different strategies up your sleeve if you want to crack these questions. I generally say this about the number system. The number system is a very important concept when it comes to the quant section of the GMAT. The number system itself contributes about 5 to 6 questions on an average in the quant section. And out of these 9 questions, or out of these 5 or 6 questions, you can certainly expect at least one question on remainders. That's what we have seen as a trend. Remainders have caught up as a topic, at least in the last decade, right? The complexity of the remainder questions have gone from difficult to more difficult. And there are more questions on remainders coming up in the quant section. So that's probably why you should be on this webinar and learn all the strategies that we discussed. All right. So with that, people, I would like to clarify the agenda for the day. I've kept about 60 minutes for discussing the strategies and the questions. I also have a 15-minute Q&A segment at the end. This is not to say that I will not entertain questions in the interim. I will definitely give you at least a minute or two in between questions, so that if there are any pertinent questions, you can ask me. But one request to all of you would be, when I'm in the middle of explaining a concept or maybe solving a question, if you have a question that crops up in your brain, it's natural. I don't deny that. If a question comes up in your brain, just hold on to that question and wait till I give you time to post your questions, right? Clearly, your questions will come up in the chat box. So I will give you time even in the interim, but I have earmarked a separate Q&A segment towards the end of the session for about 15 minutes. So all in all, I expect this session to go on till about 8:45 p.m., 9 p.m. tops. So please keep the next 90 minutes, free, and try not to, divert your attention over the next 90 minutes. If you have a mobile phone near you, it's better that you put it on silent. Otherwise, notifications can really be a distraction. A quick peek into who we are as a company. Crack Global, founded in 2006, has we have mentored more than 5,000 students. We have clocked more than 1 million coaching hours, and our students come from more than 37 different countries. That's who we are. Our objective is to connect people who love teaching to students, because that's the best fit, and we are all teachers here by choice. So that's who we are, and this is who I am. By qualification, I'm a mechanical engineer, um, and I've dabbled in multiple fields, but I've always been a teacher. I've been teaching for the last 14 years or so. I've dabbled my hands at different tests. I've taught CAD, GMAT, GRE. I've been teaching GMAT, GRE for the last 11 years or so. I've taken GRE about 11 years back when it was a question adaptive test similar to the GMAT. I scored a perfect score in quant. I got a 800 on a 800. And I've scored a 96th percentile in quant on CAT more than once. So that's who I am. That's who we are going to learn from today. And here are some free resources to get you started. As part of this webinar, we are giving out our Quant Basics course for free. So there's a link that you see on the slideshow. We'll be posting this link very soon in the chat box. So please make sure that you just copy the link and use this link to get access to a Quant Basics course without having to pay a penny. There are also some more free resources that you can access. We have our YouTube channel, Crack Bubble's YouTube channel that you can access. And we also have some free resources, ebooks, webinars, videos, and our blog. And these are all resources that you can use without having to pay anything for that resource. All right. So with that, people, I usually put this slide in one of my in all of my webinars, because I do understand that it is not necessary that all of you know the options for a data sufficiency question, because some of you might be new to preparing for the GMAT. So these are the answer options for data sufficiency questions. There are 5 answer options: A, B, C, D, and E, all of which are standard and they remain consistent. They don't change, right? So just make sure that you go through this for a couple of seconds before we actually go to the problem, because you'll be required to know these options well, like the back of your hand, so that you can eliminate options as you solve questions. All right. So these are the data sufficiency options. I hope all of you have had a good look at it. I will move on to the next and the beginning slide now. The concept of remainders is based on division. I mean, no prizes for guessing that. And therefore, the Euclidean division algorithm proposed by the famous mathematician Euclid forms the basis for us to solve remainder questions, because this algorithm is like the basis on which all divisibility concepts work, right? So that's the reason why I've put this as the first concept that we have to discuss. So as I said, it forms the basis for all the questions related to divisibility. And remainders are one of the divisibility questions. So how does it help us? The algorithm helps us in framing equations, right, which we can then use to be able to solve the remainder questions. So what is the Euclidean division algorithm? So according to the Euclidean division algorithm, if you have a couple of positive integers x and y, there are 2 more integers, q and r, where we call q as the quotient and r as the remainder. We all know this. How do we connect the 4? How do we connect the 4 integers, or how do we connect the 4 variables? We connect the 4 variables using the equation y equal to x into q plus r, right? A lot of you may remember this equation as dividend equal to divisor into quotient plus the remainder, right? That essentially is the Euclidean division algorithm. So it gives you an equation that can help you connect all the 4 components. There are 4 components: the divisor, the dividend, the quotient, and the remainder. Remember, the divisor is the number which divides, The dividend is the number that gets divided, and the quotient and remainder, I'm sure all of you understand what the quotient and remainder are, right? So what does the division algorithm say? It says dividend equal to divisor multiplied by quotient plus the remainder. And this is the component that we are supposed to find out in all remainder questions. And therefore, this equation forms the basis for solving a lot of remainder questions, right? In fact, this is one of the methods that I'll be dealing with today, all right? Note that in the above equation, you have this equation here. Please note that all the values are integral values. None of these values are decimals. None of these values are fractions. Also note that on the GMAT, remainders are conventionally considered to be positive. We have not seen a lot of GMAT questions that deal with negative remainders. But as and when we come to a question where I think negative remainders can be employed, I will discuss about negative remainders. But 90% of the times, GMAT doesn't expect you to know about negative remainders, right? There are ways of dealing with questions without actually knowing about negative remainders. So what are the important points you have to remember about the quotients and remainders? You have to remember that the quotient can be 0. So this is a very important point that a lot of test takers miss out, right? Because they assume that the quotient has to be a positive integer. It is not necessary. The quotient can be 0. And the quotient is 0 when you divide a smaller number by a larger number. Like if you have 7 and you want to divide 7 by, let us say, a 9, you can still say 9 zeros are 0 and the remainder is 7 itself, right? So understand that the quotient itself can be 0, and don't assume that the quotient needs to be a positive integer. That's one of the most common errors that a lot of test takers make. The remainder can be 0. How can the remainder be 0? I can have a number like 35 being divided by 7, and we know that 35 is a multiple of 7, and therefore the remainder can be 0. Right? So it is not necessary that the remainder has to be a positive integer. So these are two concepts that are frequently misunderstood. Right? So that is the reason why I put them at the top. And also remember that the remainder should always be smaller than the divisor. This is a very important point that will have a bearing on a lot of questions that we are going to solve today. Remember that the remainder can never be equal to the divisor. It can never be more than the divisor. The remainder is always going to be lesser than the divisor. Right? That is always a proven fact. Also remember, if the dividend is smaller than the divisor, like for example here, we took the dividend as 7, we took the divisor as 9, we understand that the dividend is smaller than 9, so the remainder turned out to be the dividend itself. The remainder came out to be 7. Why? Because the quotient was 0. So if the dividend is smaller than the divisor, the remainder will be the dividend itself. However, if the dividend is bigger than the divisor, for example, I can say 37 divided by, let us say, 8. Clearly, the dividend is larger than 8. Now, 8 fours are 32, 5 is the remainder. So if the dividend is bigger than the divisor, you see that in this case also, 35 is bigger than 7. You saw that the remainder came out to be 0. So please understand that if the dividend is bigger than the divisor, the remainder can be any value starting from 0 to 1 less than the divisor. So what do you understand from this? The biggest remainder you can get in any division where the dividend is bigger than the divisor, the biggest remainder you can get will always be 1 less than the divisor. Right? A very important property that you need to remember. The biggest remainder will always be 1 less than the divisor, because after that you will get a multiple of the divisor. Right? So these are 5 important points that I wanted you to remember before we actually move on to problem solving. Now, I also want you to understand that there are some basic rules called the remainder rules. So what are the remainder rules? There are 2 rules. Remainder of A plus B can be split up as remainder of A plus remainder of B. Remainder of A into B can be split up as remainder of A into remainder of B. How does this work? So let's take a very simple example. Let's say a small number like 123, and I'm trying to divide this 123 by 11, and I'm trying to find the remainder. So what will I do here? I can split up 123 as, let us say, 100 plus 23. That's not difficult for any of you to understand. I split up 123 as 100 plus 23. What am I going to do now? I will divide the individual parts by 11 again. Find out the remainders. So I understand that if I divide 100 by 11, the remainder is 1. If I divide 23 by 11, the remainder is 1. So how do I find out the final remainder? All that I have to do is I have to add the remainders 1 plus 1 and divide by 11 again. So if I divide 2 by 11, I know the quotient is 0 and the remainder will come out to be 2 itself. So the value of R is 2. And I'm sure all of you acknowledge the fact that if 123 is divisible divided by 11, the remainder is 2. So this is how the first rule works. If you have a very large number, you can break it up into smaller parts, divide each part by the same divisor, find out the remainders, and then add the remainders to obtain the original remainder. Understand that I could have divided 123 into smaller parts. I could have done 50 plus 23. Nothing stops me from having more parts. You can have more parts. So 50 by 11 would have given me a remainder of 6. 50 by 11, again a remainder of 6. 23 by 11, a remainder of 2, or rather 1. So my remainder would have been 6 plus 1 by 11 again. 6 plus 6 is 12, 12 plus 1 is 13. So clearly the remainder would have been 2 again. So this is the first remainder rule, which says if you have a large number, you can break it down into smaller numbers and then deal with the smaller parts. What does the second part say? The second part just tells you that if you have a large number, you can break it up as a product. So instead of a sum, I will probably use a product. So how do I break up 123 as a product? I can probably look at 41 into 3. What do I do now? I follow the same process. What is the process? I divide 41 by 11 and I divide 3 by 11. What happens now? 41 by 11 gives me a remainder of 8 because 11 threes are 33. So 8 is the remainder. 3 by 11. Remember, 3 is the dividend and the dividend is smaller than the divisor here. So the remainder will be 3 only. So how do I find my remainder? My remainder will be 8 multiplied by 3, which gives me, by the way, a number more than 11. So, right? So I'll still have to divide by 11. 8 threes are 24. 24 by 11, the remainder is 2. So, I mean, clearly we already know the remainder, right? So this is how you use the second rule. So the second rule says if you have a large number, you can break it up as a product of many numbers. And then you can deal with the individual parts, find out the remainders, then multiply the remainders to find out the final remainder. So this is what I had on remainder rules. And these remainder rules can really make your problem solving very simple in a lot of questions. When we come to that model of questions, I'll teach you how to use remainder rules in solving a question. As I told you, note that these rules can be extended to any number of terms. It's not that you have to have 2 terms. You can have 5 terms, 10 terms, right? It's as per your convenience, and it also depends on the number, of course. So consider both and take a call on how many parts you want to have. Also, don't break up the divisor. Don't break up the number in the denominator, right? If you have a 12 in the denominator, don't break it up as 4 into 3, right? It's not a good idea. Break up the dividend only, which means deal with the numerator alone. Don't touch the denominator. All right. So, summarizing what I had to say over the last 10 minutes or so, the Euclidean division algorithm forms the crux uh, of our discussion of remainders and divisibility. It helps you frame an equation which will help you solve remainder problems in a lot of cases. Remember that the remainder and the quotient can be zero. Remember that the remainder will always be smaller than the divisor, right? And when the dividend is smaller than the divisor, the remainder will be the dividend itself. Otherwise, it can be any value from 0 to divisor minus 1. We also discussed the remainder rules, right? I hope all of you are clear on this part. All of you are clear about how to use the remainder rules. As we go on to problems, as we come to certain problems, you will get a better idea of how to apply these rules, right? All right. So, what is the first method that I want to discuss, which will help you solve remainders questions? The first method is obviously using the fundamental properties of remainders, right? The properties from the slide that we discussed. We had a slide called important points to note. Those are the fundamental properties of remainders. So you can use those properties, some of those properties, to solve a lot of remainder questions, right? That's the first method. Let's take a question and see how we can utilize some of these properties. Uh, I'll have a 1 minute 30-second timer throughout this session. So for every question, you'll have 1 minute 30 seconds. That's 90 seconds starting now. Please go ahead, solve this question, and tell me what your answer is. Hold on to your answer. I'd also like to say that if you have liked what you saw for the last 10 to 15 minutes, if you have got a fair sense of the concepts that we discussed, please hit the like button. And also would like to say, please subscribe to the GMAT Club YouTube channel. There are a lot of benefits. You get access to the webinars, the live sessions, and it's a good place to be for all of you who are preparing for the GMAT. Yeah, so Pankaj, a good question. As I told you, the quotient and the remainder both cannot be both cannot be negative integers, at least in questions on the GMAT. There are questions related to negative integers, which other tests like the CAT test, but GMAT doesn't really test negative integers all that lot. All right, people. So that's 90 seconds. I hope all of you were able to attempt this question and get an answer. The correct answer on this, I'll give you the correct answer once we decipher the question. So A, B, and C are positive integers such that when A is divided by B. So when you look at the statement, when I look at the statement, my approach is to keep it simple and draw the division process. So A is divided by B. I don't know what the quotient is. Probably take it as x. And the remainder is 3. When b is divided by c, when the number b is divided by c, we don't know what the quotient is. We take it as y, but we know the remainder is 8. Now, what is one fundamental property that I'll use here to know to figure out something about B and C? You'll have to figure out something about B and C, right? Because A, B, C are all connected. The value of C will end up telling you what is the value of B, and the value of B will end up telling you what is the value of A. Therefore, your first focus should be on finding the value of C. But what kind of value do you want for C? You would ideally want the smallest value for C because you're trying to find the smallest possible value of A plus B plus C, right? Now, there is one fundamental property which we understood, that the remainder is always going to be smaller than the divisor. We discussed this, right? So look at this particular situation. This will tell you that 8 has to be less than C. The remainder has to be less than the divisor. What does that tell you? It should tell you that C has to be more than or equal to 9 because 8 is less than C. So what is the smallest value for C? The smallest value for C, let me say C minimum is 9. So do I consider 9? Yes, why not? So let's put 9 here. So now telling, what are you now telling? You're telling that I have a number B. I'm dividing this number B by 9 and I'm getting a remainder of 8. That is only possible if your B itself is 8. I mean, you can't put 7 divided by 9 and say I got a remainder 8, right? This will not happen. The only way in which the remainder can come out to be 8 is that B itself has to be 8, right? But can B be 8? Is B being 8 a possible value? Let's figure out. Using the same concept, you know that the remainder 3 has to be less than B. Remainder has to be smaller than the divisor. Therefore, you know that B has to be more than or equal to 4. So is 8 an allowed value? Is 8 allowed? Absolutely. 8 is definitely more than or equal to 4. Right? So 8 is definitely possible. So can I put an 8 here? Absolutely. The moment I put an 8 here, think about what value I can put here to get a remainder of 3. Can I put a 2 here? No, I can't. Can I put a 1 here? No, I can't. What is the only number I can put for A? The only number I can put for A has to be 3 because 3 divided by 8 gives you a remainder of 3. And you saw that in this question, a lot of students end up thinking that the quotient has to be 1 or more. Not necessarily. This is a classic example of a question where both the quotients, both x and y, were 0. Remember the constraint was on a, b, and c to be positive integers. There was no constraint on the quotients, right? So what is the smallest value for a plus b plus c? Clearly 3 plus 8, 11, 11 plus 9, 20. B is the correct answer of this question. So you saw how I used this concept. This is the only concept I used to find out the individual values for C, B, and A, right? And then find out the value for A plus B plus C. And that's why I said, using the basic properties of a particular concept, don't discount that method. That method is very important, right? That's why I put this method at the start. Right? I hope all of you are clear on this question. I hope all of you understood the explanation and the answer. So Pankaj, if you use b equal to 4, think about it. You are saying you're dividing b by 9, right? And you're telling that B, it is giving you a remainder of 8. Can you use 4 here? I mean, you can't say 4 divided by 9 gives me a remainder of 8, right? That's not possible, right? So just because B is more than or equal to 4 does not mean that you use the smallest value for B, right? You use the smallest value that fits the bill in terms of every constraint. Right? I hope that is clear now. So just because it says smallest, don't make the mistake of going for the smallest value. It may not work out all the time, right? It has to be the smallest possible value. All right, people. So let's go to the next question. The next question is in front of you. I'll again give you a 90-second timer on this. This is probably a slightly more difficult question, but go ahead, give it your best shot, and tell me what your answers are. So I hope all of you like the first question. The first question is one of my personal favorites because it's so basic that you don't have to know rocket science kind of concepts to solve it, and it's still challenging, right? So if you're liking the content that we are presenting on this webinar, please hit the like button, and that is the only motivation that that is the best motivation that you will probably give us by liking our webinar. Okay, 30 seconds more. All right, people. So that's a minute and a half, 90 seconds. Let's look at breaking down the question stem. Remember, there is a lot of data given in the question. And remember not to discount question data. That's probably the most important data in a DS question, right? Now, the question says x divided by d. Remember x divided by d. Don't make the mistake of swapping the two. That's a very common mistake that a lot of students make. So x, what kind of a number is x? The number x is a positive integer. So x divided by d gives you a remainder of 4, 24. We don't know the quotient. Let's take it as k. You can write x as d into k plus 24, but I don't think it's going to take you beyond a certain point because there are 3 variables, right? We still stick to the usage of the basic property. What is the basic property? 24, the remainder has to be less than the divisor, which means the smallest value for d, right, is 25. I can have a minimum value for d as 25. I can't go below 25, right? So this is a necessary evil that you have to consider. Moving on to the first statement, 2x, if 2x is divided by d, the remainder is 23. Is this sufficient? Let's have a look. So you now know that the divisor, right, has to be more than or equal to 24 here. According to the question, the divisor has to be more than or equal to 25. Now, out of these two, right, the stronger condition is this. You will still have to stick to the condition given in the question data, right? So you understand that the value of d minimum, the minimum value for d here has to be 25. You cannot take 24 just because you got a equal to 24 here, right? Because you can't say I divided a number by 24 and I got a remainder of 24. That's not possible, right? So when you divide a number by 25, right? If you divide a number by 25, if you're getting a remainder of 23, that's only possible if the number is 48. So if the number is 48 divided by 25, the remainder is 23. So from the first statement alone, we can make out that the value of D is definitely 25, right? Now, think about it. Some of you may come back and say, okay, what if D is 26, right? Now, if D is 26, think about it, 26 giving a remainder of 23 means this is 49. If 2x is 49, x becomes a decimal. X can't be a decimal because x is a positive integer. So we can conclude that we cannot have odd numbers here. We can only have even numbers. So D equal to 26 is ruled out. So one of you may say, okay, D equal to 27. Why not 27? Right? So let's test it. 27 giving a remainder of 23, right, gives me a number of 50. So if 2x is 50, x is 25. But if I put 25 here, will I get a remainder of 24 when I divide by 27? Clearly, I won't. If I divide 25 by 27, the remainder will be 25. And that violates the data given in the question, right? Any value of D more than 25 will continue to violate the question data. And that is the reason why the first statement is sufficient to say the only value possible for D is 25. Is the first statement sufficient? Absolutely. So my answers at this stage are A or D. B, C, E are ruled out. When 3x is divided by D, so let's look at the second statement. When 3x is divided by D, the remainder is 22. Again, we can conclude that the divisor is more than or equal to 23. But remember, according to the question, the divisor has to be more than or equal to 25. So the smallest value you can take here is 25. So let's say I take 25 here. So 25, when a number is divided by 25, I'm getting a remainder of 22. So this number has to be 72. So if 3x is 72, so 3x is 72, x is 24. This clearly satisfies the question data. However, I can also have D as 50. If I divide 72 by 50, I'll still get a remainder of 22. I'll still get 3x as 72. I'll still get x as 24. And remember, 24 divided by 50 still gives you a remainder of 24. Don't forget this. So what is the value of the divisor? The divisor can be 25. The divisor can be 50. Do we have a unique value for the divisor? We don't. So is the second statement sufficient? It is not. So D is ruled out. A is your answer. So you saw I did not apply, again, I did not apply anything complicated here. I just stuck to the fact that the remainder has to be lesser than the divisor. And using that concept, I was able to zero in on values that would satisfy the question data and the statement data, right? I also did not forget that the question data is the data that has to be satisfied by the statement data, right? If the data given in the statements violates your question data, then clearly that is insufficient. All right. So I hope all of you like this question. We'll go to so summarizing, applying the fundamental properties of remainders can really help you solve quite a few questions on remainders. So don't discount this method. This is probably the first line of attack that you can have on remainder questions. All right, what's the next method? The next method is to use divisibility rules, right? These are divisibility tests that you may have learned when you were learning the basics of divisibility, right? For example, the divisibility test for 3 says that the sum of the digits should be divisible by 3. The divisibility test for 5 says that the units digit should be 5 or 0. So a lot of people think that the divisibility test will help you understand whether a number is divisible or not. You're right, but it also helps you find the remainder, right? So leverage your knowledge of divisibility tests to solve questions and find the remainder. Okay, that's another method. So let's take a question. This is a fairly easy question according to me, so therefore I'll probably give you a shorter timer, a 1 minute timer. Go ahead, solve this question, and tell me what your answer is after 1 minute. All right, that's 30 seconds. 30 seconds more. All right, that's 1 minute. And as a lot of you may have guessed, right, we are dealing with divisibility by 5. And we know that the divisibility test for 5 is to check the units digit, right? And we also know the units digit cycle. So we have a number ending with 7. So 447, right, is a number ending with 7. And for a number ending with 7, we know that the units digit cycle is 7, 9, 3, and 1, which means a cyclicity of 4. So what do we do when we have a cyclicity of 4? We divide the power by the cyclicity. So what do? I divide 386 by 4. Do I worry about the quotient? I don't. I only worry about the remainder. What is the remainder here? 2. Because the remainder is 2, you can conclude that the units digit will be the second value. Right? This is the shortcut. If your remainder is 2, the second value will be your unit digit. If your remainder is 3, the third value will be your unit digit. So because the remainder is 2, you can conclude that 447 to the power of 386 will be a large number that ends with 9. Therefore, if you divide this by 5, clearly the remainder will be 4. So you saw how I used a couple of divisibility rules here. I used the divisibility test for 5 for the original problem, but when I was finding the remainder here, I used the divisibility test for 4. What is the test for 4? We test the last 2 digits and see whether it is divisible by 4 or not. 86 is clearly not divisible by 4, so that's a remainder of 2. So divisibility tests can actually help you find the remainders faster. You don't have to actually divide. Right? Okay. So the answer on this is E for echo. So this was a fairly simple question, and with a reason, right? I want you to understand how you can use the divisibility test to find out the remainders. You can probably look at this question now. The next question, which is probably a little harder, and try to figure out how we will use the divisibility test for 16, right, to solve this question. Because it's a little harder, I'll probably give you 30 seconds more. So I have a 1 minute 30-second timer starting now. So this is a question, I mean, as you keep solving, this is a question where you have to realize that I want you to actually work hard and find the last few digits, right? I'm not giving you the digits on a platter. I've just said it is a 50-digit number. So it's upon you to find maybe the 49th and the 50th digit. That's where you'll have to spend time. That is the phase where you cannot rush. You rush through that phase, you'll end up making a mistake in getting the last few digits. And the moment you make a mistake there, your final answer is gone for a toss. All right, that's 5, 4, 3, 2, 1, and that's time. So again, what is the divisibility rule for 16? The divisibility test for 16 says that if the last 4 digits of a number are divisible by 16, then the entire number is divisible by 16. If it is not divisible, you can still use the last 4 digits to find the remainder. So the slightly complicated task at hand is to find the last 4 digits, because I've not given you the last 4 digits. So that is where you have to exercise a little caution. So you can probably spend time on writing down the first few digits. So you know this part has 9 digits. And you know n is a 50-digit number, which means from here on, I need 41 digits more, because 41 plus 9 is 50. Right? Now, from here on, I also know that all my numbers are going to be 2-digit numbers. Every number will contribute 2 digits. So 10 will contribute 2, 11 will contribute 2, 12 will contribute 2, and so on. So if I want 41 digits, I will require 20 2-digit numbers. I'll require 20 2-digit numbers starting from 10. Therefore, what is the 20th 2-digit number? It's very easy. You just have to add 19 to 10. 10 plus 19 will be 29. So 29 is the 20th 2-digit number. So starting from 10 till 29, you can conclude that you have 20 2-digit numbers. Therefore, these numbers will give you 40 digits. But we want 41. Therefore, we bring the last digit as 3. So this 3 belongs to 30. Right? Now, what are the last 4 digits? Clearly, before 29, there was a 28. So the last 4 digits are 8293. Is 8293 divisible by 16? Clearly not. Why? Because it's an odd number. Simple. Very simple reason. So because it is not divisible, it will give us a remainder. So what is the remainder? The remainder will be the same remainder when you divide this number by 16. 16 5s are 80, 29, 16 1s are 16, 13, 133. 16 8s are 128, right? So we get a remainder of 5. and C is the answer. So I hope this has given you an idea of how to use the divisibility test to get to the remainder without actually dividing the large number, right? So two things. One, you'll have to know your divisibility tests well, and you have to understand that there are some questions where this can be applied. They won't work everywhere. If the number itself is not given, then clearly you cannot apply the divisibility test, right? You can probably use this method when the dividend is explicitly given as a number, as a value. All right. So that was my take on divisibility tests. I feel that divisibility tests always make it easy for me to find out the remainders without actually having to divide the number, right? What is the third method? The third method is obviously to use the division algorithm, the equations. But along with the equations, you'll also have to form number lists. Just framing the equations may not help you solve the problem all the time. You may hit a roadblock somewhere. So you'll have to use a combination of equations and number lists to solve the question. And that's the more difficult part. You'll have to recognize where equations will stop helping you, and from there on you'll have to use numbers, right? That essentially comes by practice. So the more questions you practice, the better you will become at identifying that particular point, that particular tipping point where you understand, okay, the equations are no longer going to help me. Let me shift to the number list, right? That comes by practice. Anyways, so let's take the first question based on this method. Slightly hard question. So I'll give you a minute and 30 seconds on this, starting now. So Abhijit, just hold on to that doubt, okay? Because we have shifted to this question. Just solve this question. Hold on to that doubt. I'll probably address that question in the Q&A segment. So this is again one of my favorite questions. I really like how this question makes it seem as though it's probably a 800 level question, whereas actually it's probably a 700 or a 720 level question. Thirty seconds more. It's 4, 3, 2, 1, and timeout. All right. Another question where there is a lot of important information given in the question. DS question again. A and B are positive integers. So I can say A, B, they belong to this set 1, 2, 3, 4, 5, 6. It's a habit that I have that when I see a statement like this, I just make a list of numbers like this, right? So that I don't miss out on details. When A is divided by 23, when A is when A is divided by 23, the quotient is 2B and the remainder is C. Very important piece of information because it tells you A dividend equal to divisor into quotient plus remainder. This is a constraint that you have to work with. You cannot ignore this constraint. Okay. First statement, when A is divided by 15, when A is divided by 15, the quotient is 3B and the remainder is 5C. Again, applying the division algorithm, A equal to 15 into 3B, that is 45B plus 5C. But this is the same A, right? I mean, it's the same number. So what can we do? We can say 46B plus C equal to 45B plus 5C. So this gives us the relationship B equal to 4C. Now we know that B is a positive integer, right? So I know that C cannot be 0. I cannot take C as 0. Also remember that this remainder, right, 5C has to be less than the divisor. 5C has to be less than 15, which means C can be either 2 or 1 or 0. Remember, we missed concluding something similar here. Remember, C has to be less than 23. So C has to be 22, 21, 20, and so on till 0. If C is 2 or 1 or 0, it clearly satisfies this condition, so nothing to worry. But the problem is, from this equation, we know that C cannot be 0, but C can still be 1 and C can still be 2. So if C is 1, B is 4, and if C is 2, B is 8. Do we have a unique value for C plus B? We don't. What is the value of C plus B here? 5. What is the value of C plus B here? 10. So the first statement alone is definitely insufficient to give us a unique value for C plus B. So first statement alone is insufficient. So at this stage, our answers are B, C, and E. Second statement alone, I'm sorry about the small typo, it had to be second. I hope all of you understood that part. When A is divided by 9, so when A is divided by 9, the quotient is 5B and the remainder is 5C. Very important to understand that 5C has to be less than 9. Therefore, C can be 1 or 0. Very important also to understand A is nothing but 45B plus 5C. Also very important to not forget that according to the question, A is equal to 46B plus C. Equating both, again we get B equal to 4C, which tells us that C cannot be 0, therefore C can be only 1, and therefore B can be only 4, and therefore we have C plus B as a unique value for 5. Why is this coming out to be unique? Because we have fewer values, and out of the fewer values, because of this equation, one value gets eliminated and we only have one value left. That has to be the answer. So the second statement alone, the second one alone is sufficient. The answer here is B for Bravo. C and E get ruled out. So this is how using the algorithm, the division algorithm, can actually help you frame equations and work with the equations and solve the question. But having said that, depending on the equations alone can sometimes be detrimental to your progress, right? They can hamper your progress. In this question, you probably do not have to use number lists. Maybe in some other question, you may have to use number lists, right? So that is something that you have to be wary of. Okay, people? So let's go to the next question now. The fifth question. Again, 5 minutes, a minute and a half on this, 90 seconds, starting now. So Atinder, just hold on to that doubt. I've already addressed that once, but since you have brought it up again, just hold on to it. I hope you're solving the current question now. I'll discuss your doubts when I come to the Q&A segment. Just hold on to that question. So 30 seconds left. All right, so that's 90 seconds, a minute and 30. So this is a question where you cannot depend on the equations alone, right? The first statement says, again, we have a mistake here. So there's a second statement. The first statement says n when divided by 6 leaves a remainder of 5. So n divided by 6 leaves a remainder of 5. We don't know the quotient, so let's take it as k. So I can write n as 6k plus 5. And this is where you have to understand that there are two variables here, there are two unknowns. And because there are two unknowns, just depending on the equation, so n is 6k plus y plus 5. So 2n will be how much? 2n will be 12k plus 10. Now ask yourself, if you divide this by 8, it is equivalent to dividing this by 8. How will you deal with the situation, right? Beyond the situation, there is no other way except using values. So our question is, if that is the case, then why not use values here at this stage itself? So the smallest value for n can be 5, right? Because think about it, if you divide 5 by 6, the remainder will be 5 only. The quotient is 0. And that's where I said, don't assume that the quotient is 1. Start off with the quotient being 0. What is the next number? The next number is clearly 11. The next number is 17. You see that every time the value is increasing by 6 because 6 is the divisor. So if n is 5, 11, 17, 2n will be 10, 22, 34, next number will be 23, 46, and so on. Now, what are the remainders? If you divide 10 by 2, 10 by 8, the remainder is 2. If you divide 22 by 8, the remainder is 6. If you divide 34 by 8, the remainder is 2. So do we have a unique remainder according to the first statement alone? We don't. Therefore, the first statement alone is insufficient. So you saw how I used a combination of equations and a number list to arrive at the remainders. I did not depend only on the equation. If I had depended only on the equation, I would have arrived at this stage, and then I would have had to break my head about what to do further. So let's look at the second statement alone now. What does the second statement say? 3n divided by 6 leaves a remainder of 3. So I'll take the quotient as k. So I can say 3n is equal to 6k plus 3. So what can I say? I can say n is equal to 2k plus 1. Right? Just dividing by 3. If n is equal to 2k plus 1, 2n will be equal to 4k plus 2. Same problem again. Because if we want to find out the remainder when divided by 8, we'll again have to plug in values. So we plug in values here only. 2k plus 1 is the general form of an odd number. So what is this second statement telling us? The second statement is essentially telling us that n is an odd number. So n is equal to 1, 3, 5, 7, and so on. Therefore, 2n is equal to 2, 6, 10, 14, and so on. You divide any of these numbers by 8, the remainders will be 2, 6, 2, 6. Same problem again. We have multiple remainders. So the second statement alone is insufficient again, which means we'll have to combine the statements. What do we do when we combine the statements? According to the first statement, the numbers possible are 5, 11, 17, 23, and so on. According to the second statement, so this is according to the first. According to the second statement, the value of n has to be odd. What happens when we combine both the statements? 1 and 2 means, what are the common values? The common values are still 5, 11, 17, 23, and so on. Were these values sufficient in the first place? No, they weren't sufficient here. If they weren't sufficient here, how will they turn out to be sufficient now? You'll still get the same answer. 2n is equal to 10, 22, 34, 46, and so on. The remainders will still be 2, 6, 2, 6, and so on. So even after combining both the statements, you still are getting multiple remainders. That's why the answer on this is E for echo. Right? I hope this is clear to all of you. I hope you're also clear about the fact that you will have to create number lists and not depend on the equation alone all the time. There are some questions like the previous one where the equations alone are sufficient, but in this question, you'll have to plug in values along with the equation. Okay? So what is my fourth penultimate method? Clearly using the remainder rules. Using the remainder rules can give you a distinct advantage when it comes to solving questions that are the expressions that are larger, right? Expressions that are big. Remainder rules will help you break it down into smaller parts. So let's look at a couple of questions now. The first question is this, a very nice question that I picked up on GMAT Club itself, right? 90 seconds starting now. So Rajdeep, just hold on to that question again. It's a very generic question. I will address it in the Q&A section. We have about 4 more questions left. So I think we'll be able to wrap up the questions. No, I have about 5 questions left. We'll be able to wrap up the question in about 15 minutes time, right? Maybe 8:50, 8:55. We can take up the questions that you have. Also, guys, I'm probably repeating this, but I don't mind repeating. If you have liked the content, if you have liked what you have seen over the last 1 hour, please go ahead and like the video, and please motivate us. Please push us to do more. It's only your likes that really keeps us going as teachers. All right, people. So that's a minute and a half. You can probably post your answers in the chat box. I'll have a look at it. P is a positive integer. What is the remainder when p square is divided by 12? Remember, if p is a positive integer, it means that p square is a perfect square. There are tons of GMAT questions where GMAT does this. What does GMAT do? It says p is a positive integer. It gives you this information. Having given you this information, it starts talking about p square, p cube, and so on. By doing this, it expects you to infer that p square is a perfect square. Because remember, guys, p cube is a perfect cube. Remember, perfect squares and perfect cubes are squares and cubes of integers, right? So when a GMAT question gives you this element and one of these elements in the same question, it expects you to infer what I told you to infer. So in this question, we will now look at perfect squares only. Okay. First statement alone, according to me, insufficient. P is greater than 3, which means P can be 4, 5, 6, any number. P square can be 16, 25, 36, and so on. Therefore, when divided by 12, the remainder can be 4, 1, 0, and so on. Clearly insufficient. Second statement, P is a prime, which means P can be 2, 3, 5, 7, and so on. So you see how the number list technique actually works very well here, right? P square is 4, 9, 25, 49, and so on. So what are the remainders? The remainders are 4, 9, 1, 1, and so on. We don't have a unique remainder, so the second statement alone is also insufficient. But has the second statement alone given us a clue? It has. It has told us that after a certain point, right, the remainders turn out to be 1 always. So when we combine both the statements, the remainders turn out to be 1. Why does this happen? What is the reasoning behind this? Because, as one of you mentioned, Kalyan, great. Any prime number greater than 3. Remember, when you combine the statements, you're telling that P is a prime number greater than 3. When this happens, remember, any prime more than 3 can always be expressed in the form of 6k plus 1 or 6k minus 1. So you're essentially telling P is 6k plus 1 or 6k minus 1. Square this. So you have 6k plus 1 the whole square divided by 12. What happens here? We have 36k square plus 12k 2ab plus 1 divided by 12. Right? You can break this using the remainder rules. You can say 36k square by 12 plus 12k by 12 plus 1 by 12. This part gives the remainder as 0. This part again gives the remainder as 0. So the only remainder will come from the third part, which is the remainder 1. Therefore, the remainder is 0 plus 1 divided by 12, which gives us 1. What happens if I change it to 6k minus 1 the whole square? Nothing happens. You have 36k square minus 12k plus 1, right? You still have the same components. This component will give you 0, this component will give you 0, and the last component will still give you 1. And that is the reason why the remainder beyond a certain point actually is only 1. Right? So when you combine both the statements, you understand that the remainder will always be 1. Right? And the remainder rules help you break down the terms into smaller terms. You saw how I applied the remainder rules here. So the correct answer to this question is C for Charlie. Any questions here, people? I hope you understood the explanation, and I hope you probably, if some of you did not know this concept of 6k plus 1, 6k minus 1, I hope you have now learned it, and I hope you will hold on to it and try to apply them in questions like these. All right, so let's quickly go to the next question now. Question number 8. Again, I'll give you a minute and 30 seconds. Starting now. Please note that it is 38 to the power of a square, right? Don't make the mistake of reading it as 38 into a square. Veena, take your time. You still have a minute. I've given you 90 seconds. All right, Leena, I understand that you may have given the answer for the previous question. I'm sorry on that. 30 seconds more. All right, that's time. So there is one crucial element that I want to discuss in this question. Whenever you have a remainder question, right, try to express the dividend, okay, in terms of the divisor, which means try to express 38 in terms of 13 or some multiple of 13. But in doing that, try to express it in such a way that it is divisor plus 1 or divisor minus 1. Because when you have plus 1 and minus 1, your remainder problems become very simple. So try to express the dividend as a multiple of the divisor plus 1 or a multiple of the divisor minus 1. Okay. So 38 to the power of a square divided by 13. So my dividend here is 38. I know there is a multiple of 13 that is very close to 38. What is that? 38 is nothing but 39 minus 1. Right? Now I can express 38 as 39 minus 1 the to the power of a square by 13. Now this is where I'm bringing in the concept of negative remainders. So you see that the remainder here will be minus 1 or 1 depending on the power, right? So on the other hand, if I had asked you this question, instead of 38 to the power of a square, had I asked you 40 to the power of a square, right? You would have written 40 as 39 plus 1 to the power of a square, and the remainder would always be plus 1. But because you have a minus 1 here, you have to be careful about the power. So let's look at the first statement now. A is perfectly divisible by 4. So A is nothing but 4, 8, 12, and so on. So what is A square? A square is 16, 64, 144, and so on. But more than that, we understand that A square is even. If A square is even, minus 1 to the power of even will be a remainder. Minus 1 to the power of even is 1. So according to the first statement, the remainder is clearly 1. Okay. So bear two things in mind. One, if you are expressing the dividend as divisor, some multiple of the divisor into k plus 1, right, to the power. If it is plus 1, the power does not matter. The remainder will be 1 only. But if you're expressing the dividend as divisor into k minus 1, then look out for the power. If the power is even, the remainder will be 1. The power is odd. What happens if the power is odd? What do we do? Can we say the remainder is minus 1? As I told you, there is no concept of negative remainders. So what do we do with this minus 1? When we get a minus 1, we add it to the divisor. Right? So remember, if you get a negative remainder, right, you have to add it to the divisor to get the actual positive remainder. The positive remainder will be 12. So remainder of minus 1 is equivalent to a remainder of 12. Right? I hope I am clear on this. So the first statement alone is sufficient for us to say the remainder is definitely 1. The problem with the second statement, people, is A's prime means A can be 2, 3, 5, 7, and so on. If A is 2, A square is 4. But if A is 3, 5, 7, A square is 9, 25, 49, and so on. Which means A square can be even or odd. So 39 minus 1 to the power of even will give me a remainder of 1. 39 minus 1 to the power of odd will give me a remainder of minus 1, which is nothing but a remainder of 12. So is the second statement giving me a unique remainder? No. I'm getting a remainder of 1 or 12. Therefore, the answer on this question is A for alpha. Right? So I hope you understood why I put this under divisibility, the remainder rules. Please understand that when you say, how did I use the remainder rules here? When you say 39 minus 1, let us say to the power of 16, right? You're telling 38 to the power of 16 by 13, right? 38 to the power of 16 by 13. Sorry on this. You're essentially telling 38 by 13, 38 by 13, 38 by 13. How many times? 16 times. So what are you saying? You're breaking up the number into smaller parts, so many smaller parts, right? And saying the remainder here is minus 1, minus 1, minus 1, minus 1. So what is the final remainder? We just multiply all the remainders. That's what we did with remainder rules, right? That's how the remainder is 1. Right? I hope all of you understood why I put this question under remainder rules. Yeah. So remainder rules are very useful, especially when you have a power. This is my preferred method when there is a power, right? So as you saw, the remainder rules could help you break down a complex, a big expression into smaller parts, and therefore help you to deal with the smaller parts individually. And that's why I like the remainder rules method. All right. So what is the last method that I want to talk about? The last method, the method that I'm going to talk about here, is the least discussed method when it comes to remainders. And this is the method of the remainder cycle. So similar to the unit digit cycle, there's also something called a remainder cycle. But the difference is the unit digit cycle is fixed. There is no change. Whereas the remainder cycle can be different in different questions. Right? It can differ based on the dividend and based on the divisor. Right? So how do we form a remainder cycle? I'll just take a simple example. Let us say I want to find out the remainder of 3 power 45, right? Maybe divided by 4, or let us say 5. How do I form the remainder cycle? Of course, I can use the unit digit cycle here, but just to explain how to form the remainder cycle, let us take the cycle. If the number is 3 power 1, right? My divisor is 5 anyways. My remainder will be 3. If my number is 3 square, divisor is 5, my remainder is 4. 3 cube, 5. This is where I want all of you to be really smart. Understand that 3 cube is nothing but 3 square into 3 power 1. 3 cube by 5 is nothing but 3 square by 5 into 3 power 1 by 5. Remainder rules. So 4 into 3. 4 into 3 is 12. 12 by 5 is 2. 3 power 4, remainder of divided by 5. 3 power 4 by 5 is nothing but 3 power 3 by 5 into 3 power 1 by 5. So therefore, 2 into 3. What is 2 into 3? 2 into 3 is 6. 6 by 5 is 1. And remember, in any cycle involving the multiplication, right? If you get 1, that is the end of the cycle. So what is the end of the cycle here? This. So therefore, what are the different remainders we can get? We can get a remainder of 3, 4, 2, 1. So now look at the power. What is the power? 45. 1, 2, 3, 4, 5, 6, 7, 8. So all the powers which are multiples of 4 will be here. So I can say 3 power 44 by 5, the remainder will be 1. Therefore, 3 power 45 will be in the first row. So you can say 3 power 45 by 5 gives you a remainder of 3. Right? So this is how you form the remainder cycle. The only disadvantage, if I can use that word here, is it takes time. Sometimes it takes time to determine the cycle. But once the cycle is known, it's just a piece of cake for you. Yeah. And remember that in the cycle, you should always try to get a 1 as a remainder, because if 1 comes up, that's the end of the cycle. Clear? So let's try this method on this question. I'll probably give you a 90-second timer on this. So a hint that I want to give you would be focus on the numbers inside the bracket and try to get the remainder as 1. That's a hint. All right, guys. So yeah, I'm really glad that uh, you found that technique useful. I have personally found that technique useful, especially when it comes to questions, remainder questions related having powers, large powers. I've also seen students getting kind of overwhelmed by numbers which have powers. So this is a technique that I give out in such problems. And I try to use this technique only when I have remainder questions involving powers. Okay, that's a minute and a half. We'll quickly go through this question. 25 power 99 into 4 power 99 divided by 11, right? I will use the remainder rules and say 25 by 99 by 11 into 4 power 99 by 11, right? And try to find the remainder of each part using the remainder cycle. Yeah. So let's say the number is 25. 25 divided by 11 gives me a remainder of 3. Therefore, 25 square divided by 11. What is 25 square? 25 square is nothing but 25 into 25. So the remainder should be 3 into 3, 9. 25 cube. 25 cube is nothing but 25 square into 25. So remainder should be 9 into 3. What is 9 into 3? 27. 27 by 11 is a remainder of 5. Don't forget to divide by 11, please. 25 power 4 is nothing but 25 cube into 25. So 5 threes are 15. 15 by 11, remainder is 4. 25 power 5, 4 into 3. 4 into 3 is 12. And I'm happy now because 12 by 11, my remainder is 1. And I know the cycle will repeat from here. So it's a cycle of 5. I have a 25 power 99 here. So clearly, will give me a remainder of 4. So this part gives me a remainder of 4. Let's take the other part. 4 power 1 divided by 11, remainder of 4. 4 square by 11, 4 fours are 16, 16 by 11 is 5. 4 cube by 11, 5 fours are 20, 9. 4 power 4 by 11, 9 fours are 36, 36 by 11, remainder 3. 4 power 5 by 11, 3 fours are 12, 12 by 11, remainder 1. Great. So 4, 5, 9, 3, 1. The cycle is 5. We have a power 99. So again, the fourth value will be the remainder. So we have a remainder of 4 here into 3 to the power of 99. 12 is nothing but 11 plus 1 to the power of 99. If you want, you can exclude this step and say, okay, 12 power 99 is nothing but 12 into 12 into 12 into 12. How many times? 99 times. Divide each part by 11, remainder rules. Each remainder will be 1. So clearly the remainder will be 1. Look out for the remainder being 1. Right? It's a frequently tested concept. Right? So I hope this method is clear to you now. I hope all of you were able to develop the remainder cycle and apply it. A lot of you gave the answer as A. Well done on that. So I have the 10th question for the day. I think this is going to be my last question for today. And please go ahead, solve this question. Slightly harder. So I'll give you a 2-minute timer on this. So I'd like to again tell you, a lot of you like the remainder cycle. It's a technique that not a lot of teachers give out, but we don't believe in holding back techniques. We believe in teaching techniques that we feel will make an impact on a student's problem solving abilities. So I hope you like that, and please click on the like button if you did like it. Okay, that's 30 seconds more, half a minute left. All right, we have an answer A, Shubham. Okay, hold on to your answer, please. All right, that's 2 minutes. And Shubham, well done. That is the answer. The answer for this question is A for alpha. And people, please pay attention on this. We'll try to develop the cycle, right? And you'll see that the cycle is fairly long. So let's start with 2 power 1, right? 2 power 1 by divided by 99. Remember, the divisor will always be 99. So don't have to keep writing it. So 2 power 1 by 99 is 2. So we don't have to keep doing this continuously, because we know that 2 power 6 is 64, right? So we know that the remainder till here will be 64 only, because the numbers are smaller than 99. It's only when we come to 2 power 7, right? What is 2 power 7? 2 power 7 is 128. Now, if you divide 128 by 99, right? If you divide 128 by 99, your remainder will be 20. 9. Now this is where you will have to be smart and understand 28 2 power 8 is nothing but 29 into 2. What is 29 into 2? 58. So it'll remain 58. 2 power 9 is 58 into 2. What is 58 into 2? It is 116. So 116 by 99 will give me a remainder of 17. 2 power 10, 17 into 2, 34. 2 power 11, 34 into 2, 68. 2 power 12, 68 into 2. 68 into 2 is 136. So a remainder of 37. 2 power 13, 37 into 2, 74. As long as we are below 99, we don't do anything. Only when we cross 99, we divide it and find the remainder again. 2 power 14, 74 into 2, 148 by 99, which gives us a remainder of 49, right? And we are arriving close to the cycle. So 2 power 15, right? 2 power 15, 49 into 2 is 98. This is the tipping point for me. Remember, 98 gives you a remainder of minus 1. So if you want a remainder of 1, remember I told you to focus on getting 1 as the remainder. So if you want the remainder as 1, you require another minus 1 here. Right? Because a minus 1 into minus 1 will give you 1. So if you require another minus 1, you require another cycle of 15 values. So you will require 2 power 16, 2 power 17, 2 power 18, 2 power 19, right? So till 2 power 30, when you come to 2 power 30, 2 power 30 will also give you a minus 1, right? So minus 1 into minus 1 will give you a 1. So your cycle here is 2 power 30. So 2 power 30 by 99 gives you a remainder of 1. If 2 power 30 gives you a remainder of 1, 2 power 99, right, can be split up as 2 power 30 into 2 power 30 into 2 power 30 into 2 power 9. Remainder rules by 99, 1 by 99, 1 by 99, 1 by 99. 2 power 9 by 99 is what? 17. So here's the answer. So this is the only disadvantage with the remainder cycle. The cycle can be long enough. But if you have an exponent-based remainder question on the GMAT, it is very, 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 very rare that you get a question like this. Your remainder cycles will generally be in the range of 3 to 6, like how we saw in the previous cycle, right? That's how they will be. But this is a very, very rare question that I again found on GMAT Club. I liked it because of the fact that it not only tells you how to frame the cycle, it also tells you how to get a remainder of 1 when you get a remainder of minus 1. Another method would be, to use the binomial theorem, but I would not recommend that because that also will end up taking the same time. And you have to understand that this method took some time for me to explain because I understand that you are learning the remainder cycle newly and I can't go fast. Okay. And dividing 99 into 9 and 11, Shubham, is going to bring in a lot of confusion. I told you, try not to divide the divisor by, try not to split the divisor, right? It always brings in a confusion. Always try to deal with the dividend. Don't tamper the divisor, right? And I also want to tell you that I did not give you 1.5 minutes on this, Shashank. I gave you 2 minutes. Okay, all right. So I hope the remainder cycle method is clear to all of you. don't expect this question, this kind of a question to come frequently, right? Expect questions like the previous one to come more frequently. And you saw how remainder cycle made your life much easier in such questions. Okay. So with that, I will now move on to the Q&A segment, people. So if you have any questions, um, I would like to answer them. I'll start with answering Barry's question. Is it a good idea to memorize the remainder from 2 to the 12th power of 2? You can't do that, Barry, because the remainder depends on the divisor. However, I think I got what you wanted to ask. It's a good idea to memorize the powers of 2 till 12. Like I remember 2 power 12 is 4096 because I've used it so many times. So it's a good idea to memorize, let's say, powers of 2 till at least 2 power 10, powers of 3 till maybe 3 power 8, powers of 5 till 5 power 6. Because then it means that you don't have to, rake your brains to find out, okay, what is 2 power 12? Your problem solving will become faster. Yes, people. We can go ahead with any questions you might have now. I'll probably allocate about 5 to 10 minutes more for the questions. So please go ahead with your questions, people. I also hope that all of you have made note of the link that we have given. You can use that link to log on to our website and use that link. You'll get free access to our quant basics course. And our quant basics course is pretty comprehensive. It really works well for all of you who feel you're not all that good at the basics of quant. No, you cannot use the pen on the whiteboard, Bindu Madhavi. That's the catch, right? That's why the online whiteboard is a challenge, right? You can only use the mouse. I mean, all of us wish we were given a pen, but that would have been that would have made our life infinitely easier. But that is not there. Shashank, we do conduct webinars. We conduct webinars, our own webinars. We also conducted webinars on GMAT Club, right? I think we have conducted at least a couple of webinars on GMAT Club related to number systems, number properties. This is the second one. I think we conducted one in January. We tend to cover diverse topics because we don't want to stereotype ourselves into one topic, right? We Yes, definitely we conduct webinars on different quant topics. Shashank, I hope that's answered your question. All right. So guys, if you just scroll up, all right. So just give me one moment. Just give me one moment. I'll copy paste the link here, and all of you can make note of the link. All right, people. So this is the link. I hope. No, Rajdeep, there is no rule that they will give you a question that is less calculation intensive. That is not there. That is not a case at all. So I mean, you can't expect that to happen. Just give me one moment, guys. All right, people. So it seems like I'm not allowed to post any link. So we'll make sure that the link is posted in the chat of this webinar in due course of time. And maybe you guys can come back and make note of the link maybe tomorrow, right? It was posted at the start of the session, but I think the chat has moved to a certain stage. I'm not able to find it. Any other questions you have for me, people, on this webinar that I conducted? Any questions at all related to the topic? General questions related to the GMAT? Please go ahead. Feel free to ask. Every question, according to me, is a good question. All right, people. So if there are no other questions, then I'll probably have to call it a day here. I thank all of you for being really patient with me on this webinar and being patient with me on the small formatting errors that I've done on some questions. Thank you for accommodating those errors. I hope I've given you some uh, really interesting and useful techniques for you to employ when you are dealing with remainder questions. I hope I've made it um, easier for you to now deal with remainder questions, because that was the objective, to help you guys not get overwhelmed by remainder questions, because in our experience as quant teachers, question on remainders are typically one category of questions that can trouble students. So I hope this session has in some way um, helped you overcome that some sort of fear or repulsion that you may have had about remainders. And I hope it has given you enough confidence to go ahead and try as many questions on remainders as you want, right? Um, with that, I would like to thank all of you again, and I wish you all a very nice evening ahead. And please stay safe. And please don't forget to like these videos and like these videos. And please don't forget to come back tomorrow into the chat window and have a look at the Quant Basics, the link for the Quant Basics course. All right. Okay, people. So with that, I'd like to call it a day. Thanks a lot. All right. Good night, people.